So the process of nitration is really similar to halogenation and sulfonation. Let's take a look at the overall mechanism, and then I'll show you guys the mechanism for it. So the overall transformation involves taking an aromatic compound, treating it with nitric acid, which is HNO3, and H2SO4, sulfuric acid. When you do this, you can pop on a nitro group, and it's important to remember that a nitro group is a little bit weird because it's got a negative charge and a positive charge on it. What do we call these compounds? Zwitter ions. Yeah, Zwitter ions are compounds that have both a positive and negative charge but are overall neutral. So nitro groups are unique that way. Let's take an example, the most famous example for nitration. We're going to take this aromatic compound. What do we call this? Toluene. And we're going to nitrate it. Oop. And in this case, we're really going to overdo it. We're going to add excess. And when we do this, your nitro groups will get installed in 3 different positions. And we'll talk more about the regiochemistry of electrophilic aromatic substitution later, but it has to do with the electron donating group or electron-electron group on the aromatic ring. What is this molecule called? TNT. Exactly. So this is the way that TNT is primarily manufactured, is just by nitrating toluene. It is a little bit problematic simply because TNT is a relatively unstable compound. Ultimately, if you work in the military or in any sort of field where you use explosives, they're shifting away from TNT as their main explosive using things like C4. C4, I don't know if you guys are familiar with it as an explosive, but you can actually catch it on fire and it won't explode. There are stories of people in Vietnam using it as fuel for like cooking. It's really, really inert, a lot safer than TNT. So this is kind of an old school explosive. All right, let's take a look at the mechanism. And the mechanism starts out with our nitric acid. And again, actually, let me show this bond here. Nitric acid is unique because it is a Zwitter ion. And we've got this nitric acid mixed up with sulfuric acid. What do you think the stronger acid is? Sulfuric. Sulfuric acid, if you think about the conjugate base, it can share the negative charge across a wide area. So sulfuric acid is kind of our benchmark for super strong acids. In this case, what's going to happen is the alcohol on your nitric acid is actually going to get protonated from sulfuric acid. A stronger acid wins here. Okay, and at this step we've got this really, really high energy intermediate. It's not very happy, but we've got a good leaving group on here. What do you think can happen next?
Just falls off.
It can fall off on its own, or even better, it can get shoved off. So in this case, this negative charge can clamp down and shove off this water as a leaving group. When we do this, we create a really important intermediate. This intermediate is referred to as a nitrosonium ion. And the reason we have to form this intermediate is we have to make something that's an exceptionally good electrophile in order for electrophilic aromatic substitution to occur. If we look at this nitrogen, it's a really, really good electrophile. So let's go ahead and have this react with our benzene ring. It's going to attack this nitrogen and then kick up electrons onto an oxygen.
Is that the carbon on top attacking or the carbon on the side?
As a nucleophile? That's a good question. So in this case, it's just the pi bond. So it could be either carbon. It really doesn't matter. Any carbon on the ring will react. Yeah, if you look at this, right, an aromatic ring, you could also draw it as a circle. It doesn't matter which position because the whole ring itself is electron rich from that delocalization. So I'm fine with you drawing it in any position. It's really not wrong to do it either way. Okay, so now we've got the sigma complex. And last but not least, that water that was kicked off in that first step can act as a weak base. It can grab this proton and clamp down, giving you your final nitrated product. This is one reaction you guys will actually do in your synthesis project starting next week. It's a fairly stubborn reaction. It can be quite messy, giving you black tar. So when you do this in lab, you have to add things very, very slowly, meaning drop by drop, and oftentimes you do this in an ice bath. If it gets too warm, it tends to decompose pretty rapidly, and so I will warn you guys in lab to be extra, extra cautious and try to monitor your temperature as much as possible. The reason the temperature rises so rapidly is we were basically mixing a ton of super strong acids together. Anytime you're doing acid-base chemistry, you tend to run into exotherm problems. Does that make sense? Yep.
Can I ask a question about further up? On the left-hand side, why is it that the alcohol is getting protonated and not the oxygen with a negative charge?
That's a good question. So Grace was asking, why doesn't this oxygen grab the proton instead? The reality is it's a complex equilibrium. However, if that oxygen were to grab a proton, it doesn't go in the forward direction. It's just kind of stuck at that point. But you would have some of that present in solution as well. By protonating the alcohol, that turns it into a leaving group and then allows the reaction to proceed forward. Yeah, oftentimes with these acid-base equilibria, there's a lot more going on, but we don't bother showing it because it's not anything useful for us.
So this is saying if it does proceed by this route, it goes all the way to here.
Yeah.
Whereas if it goes the other way, that's just a dead end.
Exactly. If you protonated that oxygen, you're kind of in a dead end.
Okay.
Yep. Okay, so there's another cool trick you can use with these. Once you nitrate a compound, it is really, really easy to turn a nitro group into an amine. What do we call this product?
No, anisole.
No. So it's aniline, not anisole. Anisole is methoxybenzene. I know it sounds really similar, but this is aniline. So we can make aniline derivatives from nitrated compounds. Oop. And this is actually a super straightforward and easy reaction to run. All you need to do is take hydrochloric acid and iron or zinc, and you can easily convert your nitro group into an amine. This amine can be a nucleophile. It can do all sorts of unique chemistry. And this is a pretty common reaction, and it's a useful synthetic tool. However, one thing that's kind of tricky is that these anilines tend to decompose pretty quickly, so oftentimes this is the last step in your synthesis if you can avoid doing this early on. Does this whole procedure make sense? This last mechanism, I don't expect you guys to know. It's just a reduction mechanism. It's a little bit more complicated than is necessary for this course. All right. Now we're doing some cool reactions. Friedel-Crafts alkylation is our next one. So let's take a look at a Friedel-Crafts reaction. I'm just going to abbreviate this as RCl. What do you think the R is? It's an alkyl group, right? And we'll talk about the appropriate alkyl groups that work best for the Friedel-Crafts alkylation reaction. Typically, you want this R group to be a tertiary carbon, and I'll explain why. And then again, we're going to use aluminum trichloride as our catalyst. And when you do this, you can basically add an alkyl group directly on to your aromatic ring really easily. This is a very popular reaction. Okay, so now let's take a look at the mechanism. So I'll use terbutyl chloride, and we're going to react this with our aluminum trichloride, which we know has that empty p orbital, which makes it a really good Lewis base. What do you guys think the first step is going to be? Yep. Fill the orbital. I'm not going to show stereochemistry on the aluminum. However, it is important to remember that it's tetrahedral now. Okay. Whoops. Holy cow. Sorry about that. I'm getting stuck on halogenation. Let me clean this up a bit more. I don't like the way it looks. Okay, so now we've got this terbutyl group hanging off the end. This is relatively unstable. It's not very happy as is. So what ends up happening is this covalent set of electrons will hop over and give electron density to that chlorine. And I'll just write AlCl4 is our other byproduct here. Why does this work better if you've got a tertiary alkyl halide? Yeah, the carbocation is more stable. What happens if you use a secondary alkyl halide?
You would want to rearrange it.
Yeah, it would definitely rearrange. Primary, definitely rearrange. So if you run into this problem where you're making a carbocation that can rearrange, it most likely will happen, and you want to avoid that as much as possible. So typically we use tertiary alkyl halides. However, you can use something like ethyl chloride. Why will that work?
Can't rearrange.
Yeah, it can rearrange, but it still forms the same carbocation, right? So you're kind of stuck in a loop at that point. So try to focus on forming a carbocation that is what you want it to be. Okay, next step, we've got this super good electrophile, our carbocation. And the benzene is going to attack that carbocation. We're going to form our sigma complex. And we still have this aluminum complex floating around that we know can act as a weak base. So just like before, this chlorine is going to act as a base, grab a proton, clamp down, and give you your alkylated product. And then your other byproduct is HCl here, right? Like I said, the main thing you got to watch out for is rearrangements. That's the number one mistake I see people make, is they use an incorrect alkyl group, and it would rearrange and you wouldn't get your desired product. We'll talk about workarounds to install alkyl groups that aren't tertiary or would otherwise undergo rearrangements.
If you're doing synthesis, would be if you wanted something like a product that comes from rearrangement, could you use that?
You can, however, first term I told you guys if something can rearrange, it will rearrange. The reality is a little bit more complicated than that. Most of the time you'll get a mixture of your product before and after rearrangement, right? So ideally as a chemist, you don't want byproducts. You want to avoid it as much as possible. Does that make sense? And I'll show you guys an example of that. So let's just take an easy example. I'm not going to show the full mechanism. So let's say we use 1 chloropropane and aluminum trichloride. You would end up with a mixture of different products. You would end up with one product where the propyl group is installed as you would expect, and your other product would be your rearranged product, right? And you can do this experimentally, and the ratio is 35%
I think
to...
I have too many carbons.
Oh, sorry, thank you. To 65%. So you can see you mostly get rearranged products, but you do get a little bit of the unrearranged product. Does that make sense?
Can you stop from doing the non-rearrangement one?
Not easily. I'll show you guys a good workaround for that shortly, though. There's another reaction called the Friedel acylation, and then we can do subsequent chemistry on that to ideally get more of this product than that product. All right, there are a lot of limitations to this reaction, though, so we have to come up with our laundry list of situations where it won't work or where it will cause problems. So, limitations. First one we already covered is that primary alkyl halides will rearrange, with the exception of an ethyl group, right? And if an ethyl group rearranges, you still have an ethyl group. It doesn't matter. The second thing is that it only works for sp3 hybridized carbons. And what I mean by that is, let's say you've got an aromatic ring that you want to do a Friedel-Crafts reaction on, and you say, you know, I want to install this alkene. This reaction will not work. There are various techniques to get this reaction to work involving organometallic chemistry, but we're not going to cover most of those in this class. So you do have to watch out for that. You need to have an sp3 carbon coming off of your chlorine. The third problem, which is arguably the biggest problem, is that alkyl groups are activating. Does anybody know what activating means? Yeah, it's usually something that promotes the reaction, right? An activator. Another way of thinking about this is last term, I said an alkyl group coming off of an aromatic ring is slightly electron donating. And why is that? Yeah, hyperconjugation, right? As soon as we append an sp3 hybridized carbon, it's going to dump in a little bit of electron density, which kind of amps up the nucleophilicity of that aromatic ring. So alkyl groups are activating, which often leads to uncontrollable over-alkylation. So I'll show you guys what I mean. Let's say we've got this benzene ring, and I react this with tert-butyl chloride and aluminum trichloride. We can install this tert-butyl group, no problem, right? The problem is when we're looking at this aromatic ring versus this aromatic ring, the one on the right is more nucleophilic. It has more electron density on it, right? So this is a stronger nucleophile. And if there's any aluminum trichloride, or sorry, if there's any of our starting material left around, it will quickly grab that before the benzene has a chance to, and it will install another tert-butyl group on there. Even if you only add one equivalent, it will be very sneaky and try to soak up all of that starting material that you have. So oftentimes you end up with a mixture of monoalkylated and dialkylated products. So you have to watch out for that. Does that make sense? There are ways to prevent this as much as possible using strategies like blocking groups that can help limit overalkylation, but it is something you have to pay attention to. The last one involves kind of the opposite circumstance. Strongly deactivated rings just simply don't work. And a strongly deactivated ring is something that has some sort of electron withdrawing group on it. And so I'll show you guys an example. Let's say we have already installed a nitro group, and I want to now add in an alkyl group onto the aromatic ring. This simply will not work. So it doesn't matter how much we push it. We'll just kind of stare at your starting materials and say, yeah, no, thank you. And that's simply because this nitro group is too electron withdrawing. These are the common pitfalls that people run into, especially as we get further on in the term. It's easy to forget that if you have an electron withdrawing group, that synthesis strategy won't work. So oftentimes you have to devise a route that will avoid the installation of your electron withdrawing group until later on in your synthetic scheme. Does that make sense? Okay, there's one other Friedel-Crafts reaction. It's similar, but this is an acylation instead of an alkylation. Again, we'll do the overall reaction, and then we'll do the mechanism in a second. Okay, in these reactions, you're going to use an acid halide. So in this case, 99% of the time you'll see a chlorine coming off of that carbonyl. You can do this with bromines, however, those starting materials are so reactive that typically people just avoid them. And in this case, you use AlCl3 as your catalyst again. And you can imagine, just like before, you can append your new group on. In this case, your R group is an alkyl group, so you're basically making a ketone, right? If that R group were a CH3, what would our product be called? So if R is a CH3. Yeah, acetophenone. So you can make acetophenone this way from benzene. The reason this is called acylation is these groups are called acyl groups. So it's a really nice strategy for getting a ketone derivative. Let's take a look at the mechanism. The mechanism at this point is getting pretty redundant. We've got this p orbital. What group do you think is going to attack that p orbital? Yeah, the chlorine in this case will. Okay. That chlorine doesn't look very happy to me. What do you think might happen next? Yeah, it'll fall off, just like with our alkylation reaction. So in this next step, we're just going to dump electrons over to that chlorine. And now we're going to make something that looks very weird. When you do this, this carbon now has a positive charge, but what's special about it? Resonance, right? So we're not used to seeing these, but you can take one of these lone pairs, dump it down, and you can draw the resonance structure. So now this oxygen's got the positive charge. So really that positive charge is shared between carbon and oxygen. What's the major resonance contributor? Ooh, first term stuff.
Well, the alkynes, it doesn't destroy the octet.
So the triple bond or double bond?
Triple.
Triple bond, why?
Because
Full octets.
octet rule, yeah.
Octets take priority, right? The one on the right has full octets on every single atom. The one on the left, the carbon doesn't have an octet. It's very, very counterintuitive because people will say oxygen doesn't want that positive charge. Why would that be the major contributor? Octets take priority, right? So this is our major contributor. All right, now that we've got this super strong electrophile, we can react this with our aromatic ring. And this can tack this carbon and then kick up electron density onto that oxygen. Alternatively, you could have it react with your other resonance structure. It doesn't really matter, right?
And that one's before, okay?
Yeah, it's important to remember with resonance structures that they're a hybrid of the two, but the one on the right is a better descriptor of what's going on. The oxygen's carrying more of the positive charge than the carbon. Yeah. Okay, so at this point, we're going to make our sigma complex. All right, and then we've got this aluminum tetrachloride, I should say, floating around that we know can act as a weak base. And this will help restore aromaticity to the system by plucking off this proton, giving us our acylated product. The other thing too is, I know we're kind of running into a lot of new terminology, but you'll hear this key intermediate referred to as an acylium ion pretty regularly in your textbook. It's a super powerful electrophile, and it's a really nice way of doing electrophilic aromatic substitution. The cool thing with the Friedel-Crafts acylation is we've installed a functional group, and do you think this is electron withdrawing or donating? Withdrawing. There is no way for you to do a resonance structure where you push electrons into the system. However, you do have resonance structures where you can pull electrons out of the ring system. So this is electron withdrawing, which means it's not going to overdo it. It's only going to add that ketone into one position. It won't add it into multiple. So your acyl group is electron withdrawing. Which prevents over-acylation. Does that make sense? They're two very, very similar reactions. I think there's a... We're going pretty fast today. Sorry, I'm kind of cruising through here. I'll show you guys a cool variant of the Friedel-Crafts acylation reaction to get around that problem of installing primary alkyl halides. This is referred to as a Clemmensen reduction. And let's kind of go over our previous problem. I want you guys to predict what products you would get out of this reaction. I'm just going to draw my skeleton structures and then we'll add on the substituents. And give me a thumbs up if you think you got it. Okay, so for this one, like I said, you can get a little bit of your anticipated product, but it will mostly rearrange and give you this product. Which one do you think we're going to get more of, the left or the right? The right, exactly. So we'd get about 35% of this and 65% of that. So the question is, well, what if we want more of this? We don't want to throw away 2/3 of our product, right? So what you can do is you can use this Clemmensen reduction trick. And this is good for two different reasons. The first one is it prevents forming that undesired product. What's the other problem we have when we do the alkylation? Yeah, I could add a second equivalent to the other side. So instead what we do is we count our carbons and we pick an acid halide with the appropriate amount of carbons. So you see in the top one how we have 4 carbons. The bottom one we have 4 carbons. Make sure that they match. And again, we'll use aluminum trichloride. We're not there yet, but this is good. It won't over-acylate. You'll only add 1 ketone. And now what we can do is do a super green reaction involving a zinc-mercury amalgam and HCl. And you end up with only that alkylated product. The nice thing with this reaction is you guys don't need to know the mechanism. It gets into organometallic chemistry way beyond this class. So if you do want to install a primary alkyl group off of your aromatic ring, the Clemmensen reduction is an excellent way. And oftentimes people purposely do the Clemmensen reduction to avoid that problem of overalkylation too. So it's kind of a double win in that regard. Make sense? All right. We have 10 more minutes, so I'm going to jump into the next section.
Is that catalytic mercury? Is that right?
No, with mercury amalgams, they oftentimes show it bracketed like that. We're not going to get into metallic chemistry, but it's very weird. If you go on and you take inorganic chemistry, you'll cover more of that. Okay, one more section today. Let's talk about activators. We already talked about activators a little bit, but what does it mean when something's activated?
It starts reactions.
Starts reactions. In the case of electrophilic aromatic substitution, does it mean we have an electron donating group or an electron withdrawing group? Donating, right? So activated molecules have electron donating substituents. Oftentimes I refer to these as EDGs for electron donating groups. So if you ever see me shorthand that, that's what I mean. Let's take a look at strong activators, then we'll go to moderate activators and then weak activators. So strong ones are ones that can really donate electron density to your aromatic ring. And the easiest way to identify your strong activators is they have lone pairs on the atom that's directly attached to your aromatic ring. So just 1 second. Have lone pairs on atom attached directly to aromatic ring. So let's take a look at some examples. What's this compound called? Phenol, or hydroxybenzene, if you want to go old school or not follow normal nomenclature rules. All right, what I want you guys to do is to draw the resonance structures, all of the resonance structures for phenol.
Oh my god. Duplicate resonance structures.
And then if you think you got all the resonance structures, give me a thumbs up. Show of thumbs. All right, let's go ahead and push electrons here. So we can push electrons down, and I can push electrons over to that carbon. What would we call it, or what do we call that carbon that's right next door? Is that the ortho, meta, or para position? Ortho, right? So in this case, we've got a charge on that ortho position. We can keep on pushing this around. What do we call it if we have the charge on the opposite side? Para. And then we can take this charge, clamp it down, kick it up. And what position are we at here with the negative charge? Ortho.
Isn't that the same as the first resonance one?
Yeah, they're similar, right? They're called degenerate resonance structures because of that. However, it is important to remember that all three of those carbons are sharing that negative charge. So if we think about this aromatic ring doing a nucleophilic attack, those carbons are the most likely carbons to do the nucleophilic attack, right? Because that's where the electron density is. So typically when you have a strong activating group and you do electrophilic aromatic substitution, it's your ortho and para positions that are going to be the ones attacking. So phenols are really common strong activators. Let's do a couple others. I won't force you guys to do all of the resonance structures. Phenoxide is a really strong activator, simply because when you do this, I'll draw the hybrid really quick. Actually, let me just draw it all dashed like that. This oxygen has a partial negative, your ortho position has a partial negative, para is partial negative, and that other ortho position is partial negative. Strong activator. Does anybody have another one that they might think is a strong activator? Anisole. So anisole is pretty similar. It's got those two lone pairs over here. So phenoxide, anisole. Any others?
Aniline?
Aniline, exactly. If you look at aniline, the nitrogen that's attached on the ring has a lone pair. This is also a really strong activator. The key thing with all of these is that that atom directly attached to the aromatic ring has a lone pair that can dump electron density in. There are some that are a little bit trickier, and these are called moderate activators. So let's say we've got an ester and your ester looks like this. This oxygen that's directly attached to the aromatic ring could donate its electron density into the ring, but why is this a moderate activator?
You could also withdraw with the double bonded carbon oxygen.
Yeah, exactly. If we look at this lone pair, it also has the option of pulling electron density towards the other oxygen. So this isn't as good of an activator as the ones that I just showed you. These are moderate activators simply because they have competing resonance. So oftentimes esters like this are moderate activators. You could have things like amides that fall in the same sort of class. Where this lone pair coming off that nitrogen could go either way. It's moderate. There are a lot of these. So anytime you have a lone pair that has competing resonance, think of it as a moderate activator. One last one, and then we're done. These are weak activators. Things with alkyl groups coming off of them. Why are these weakly activated again? Yeah, weakly activated due to hyperconjugation. All right, so tomorrow when we come in, we're going to change gears and talk about deactivators, and then talk a little bit more about the regiochemistry determination when you've got both activators and deactivators on your aromatic ring.